Okay, we are at 5 p.m. sharp in UK time. We are moving to the next speaker. Dr. Christopher Rackauckas is from MIT and also Julia Programming Language. I know him because of several of interesting talks that he had. I was not lucky enough to be in person there, but I saw them online and I really enjoyed. So I thought of inviting him for this event as well. It will be very useful for our students. Dr. Rackauckas, you can go ahead. You are muted.
Oh, are you able to hear me now?
Yes, perfect.
Yeah, let me just double check that I'm on the right mic because there's one that sounds a lot better than the other ones. Yeah, okay, this is the good one. Okay, cool. Yeah, thanks for having me. Yeah, I give a lot of different talks on a lot of different subjects, and this is one that I haven't been talking about as much yet. But since I saw the title of being future algorithms, I thought, well, why talk about the stuff that I've already done in the past? Why not talk about the future algorithm? Yeah, so this is actually one of the earlier talks on what's kind of becoming one of the new sets of talks that we're doing. So, there's a bit of newer slides, newer stuff, a lot of untested slides here. Fingers crossed that they work out and are good at explaining this, but also that means that you get the new stuff early. And this new kind of direction is what we call symbolic numeric methods, right? Cheating for robustness and speed. And I'm going to explain this in a lot more detail, but what I really mean by this is that there are numerical methods, right? There are things that can solve, ODEs numerically. There's Newton's method that solves, root finding problems numerically, and those are good. But and a lot of what I've done as a numerical analyst has been to keep on improving these algorithms, right? You make them faster, you make them more robust, and yada yada, just by finding different ways of building better ODE solvers, right? But it turns out that there's just these other types of algorithms which we call symbolic numeric algorithms, which basically what you do is you just say, well, if we change the problem, we can solve it better, right? And you even probably do this implicitly a lot, right? So you probably have gone to use some ODE solver, and then someone in your field says, oh, actually, in our field we don't use this one, we use this other way of solving equations. It just happens to be better in our field, right? And so the question here is that, can we make it so that the way the libraries actually do that, right? Like when you say like, oh, I can't use a library because it does the generic thing. Well, does a library doesn't necessarily have to do the generic thing. What kind of math does it have to do? So that way it will do the specific thing for your specific domain and actually be that much faster, right? That's what I mean by this cheating for robustness and speed. Can we make it so that way before we do the numerics, we actually change the problem that we're numerically solving to end up with something that's easier to numerically solve as part of this process, right? And so if you want to connect with this and you want to get a lot more of the story, I'll show this more at the end. But a lot of this deals with the Julia SciML organization. If you go to the sciml.ai, you'll find a lot of these. You'll find a lot that describes the SciML tools. You'll find the documentation right here, docs.sciml.ai. That goes into a lot of the tutorials about the different pieces I'll be talking about, with a lot of what I'm talking about here being what's in this newer library called Modeling Toolkit. And yeah, so so this is where you'll find everything, but we'll come back to this at the end when you have questions. So first of all, let me go over a bit of the SciML organization and what are all the different types of algorithms that we work on, what are the, to be able to set the groundwork for how symbolic numeric algorithms fall into this. So the SciML open source tooling for modeling and simulation, it really focuses on getting speed, stability, stochasticity, adjoints, and parallelism, right? It's basically this concoction of if you want models that are big, fast, and are solving well, those are all the things that you really need to consider, right? And so a lot of what we've done, especially in the past, has been to work on such, numerical methods, right? So one of the big things that we're known for is things like differential equations.jl, which is a new differential equation solver library that we've been repeatedly able to show, for example, that it's 50 times faster than SciPy, 50 times faster than MATLAB, 100 times faster than RSDE-solve, and it also outperforms even some of the classic C and Fortran methods. And so for different reasons for each of these cases, right? And this is kind of good to make clear, right? Against a lot of the Fortran or a lot of the methods like R, Python, and MATLAB, there's a fundamental difference in terms of the compiler, the interpreter, and the language semantics. There's an overhead due to how the software is done that makes these so much slower, right? And so, being able to get rid of those is one aspect of the computer science to make it faster. But then outperforming the C and Fortran methods is more of like an algorithmic thing, saying, like that the CVODE method and LSODA are actually not very good for this type of problem, right? They're about 10 times slower to get the same amount of error, and it has to do with certain behaviors of explicit ODE solvers and certain behaviors they could specialize on, right? And also for stiff ODEs, there's also new algorithms like Rosenbrock methods, yada yada, that can outperform LSODA, CVODE, and these BDF methods, right? So for stiff and non-stiff equations, we've been developing lots of new algorithms over time. There's about 100 contributors per month across the SciML different repositories. We have a paid summer program that trains about 10 devs every year. There's a Julia Lab at MIT that we run, which is about 20 people doing data-driven kind of development of new algorithms, right? So there's like 130 or so different people that are working across this organization that we run. So there's a lot of research coming out on new algorithms all the time because of this. And one of the ones I want to highlight that has actually been new within about the last year or so here has been this nonlinear solve, right? Nonlinear solve has, you can already start to see a little bit of the symbolic numericness in this because, so the nonlinear solve is a library that's just for root finding, right? So, it's like the equivalent to what you'd find as like fminCon in MATLAB or SciPy's Newton algorithms, right? And so if you look at a graph here, right, you go like, okay, like everyone has everyone has a root finding out. Everyone can do Newton's method, right? But there's some interesting things here that you'll find inside of here, right? One is that, for example, it's able to have this sparsity kind of handling, right? Where you'll find that for very large problems, using this sparsity ends up giving you orders of magnitude faster than sundials or MinPack. MinPack is the algorithm that's actually wrapped by MATLAB and SciPy as well. So this is kind of like this line right here is like the Python, R, and MATLAB line, right? This is like the C line with the sundials, right? PET-C is also in a newer version of this benchmark, and it's around here. And so we're getting like, order of magnitude or faster than like PET-C and these other things, right? And you're like, how could you even do that, right? Because it's just a simple Newton algorithm, right? Well, there's some differences, right, in terms of the line search algorithms, in terms of certain things to do with trust regions. But one of the biggest things involved in this is actually automatic differentiation and sparsity detection, right? So if you ever use a root finder in something like Python, they'll say like, yeah, if you give us a sparse matrix, then we will use that to make the solve better, right? But what I'm going to show you here is that what we've done with this library to be able to get that order of magnitude better is that we don't require that from the user. We can actually just look at your code and figure out the sparsity pattern and specialize on this and be able to build a better solver. And so we can show that these solvers are very robust because when something is actually supposed to be zero, we actually get truly zero because the compiler is actually forcing things to be zero, not like numerically making things zero. And so it makes things a lot more robust and it makes things a lot faster. And I'll go into a bit more detail on this, right? So what we kind of cover in the SciML organization is linear solves, which is, AX equals B, solve for X, right? Nonlinear solves, find U such that F of U is equal to 0, solving ordinary differential equations, stochastic differential equations, delay differential equations, differential algebraic equations, nonlinear optimization problems, nonlinear integrals and quadratures, and also partial differential equations, right? If you peruse around the docs, you'll find that there's solvers for all of these types of different equations, that we have all these different automated solvers, the tolerance. So if you want to put it as a simplified thing, you'd say like, oh, it's like the MATLAB standard library, or it's like SciPy, right? Except with performance, with performance, parallelism, more robustness, and then also one of the major aspects is scientific machine learning. Now, this talk is not about scientific machine learning, but it is a crucial enough piece to the library that I do want to give a quick introduction to it. And it's the idea that all of our techniques for doing, robust solvers and building models and such, what we want to do is we want to make sure that it's always compatible with neural networks and automatic differentiation. So that way, if you want to mix the world of machine learning with the world of scientific computing. You can do that trivially using these kinds of solvers, right? So your standard ODE solver, you can't train a neural network inside of it, but for these solvers, if you use it with a machine learning library, like if you put the ODE solver as a hidden layer or an activation function, it will just work, right? It's designed to be connected with it. And the reason why we do this is for all these kinds of workflows, like for example, doing automated model discovery in physics. So we can do things like, for example, write down a mathematical model, like an ordinary differential equation that describes a physical system, right? But we can say, hey, this is the physics that we know, but maybe there's a physics that we don't know. For example, like a friction term that we don't understand, right? We model the world with spherical cows, and there's no friction, there's no drag due to air, right? But then in the real world, we have data, we find these things, and can we uncover what physical terms we were missing? What is the physics that we didn't actually put in our equation? Can we automatically identify that from the system? So we have a whole way to be able to, inside of the ODE solvers, you put neural networks, and then you do this sparse identification. It actually gives you out the equations for what you didn't have in the model. So one nice example of this was with chemical reaction processes. So here, for example, we have a partial differential equation. This ANN is a artificial neural network that was put into the equations. So we have this system where we have a fluid flow that is diffusing and advecting. We know the diffusion rate, we know the advection rate, but for the two different chemicals in the system, we don't actually know the chemical reaction between them. And so what we can do is we can use data from the system to be able to learn from a very short time series how the chemical reaction works. And once we learn the chemical reaction, then we can actually predict out what the future is going to be. And what we show is that we can actually use this in a way where we're actually able to spit out predicted equations for what are the equations you did not, So if you write down this advection diffusion system, you say, okay, I don't know what the reaction terms are, but let's make the reaction terms be a neural network. You train the neural network, and then you use the sparsification, and it tells you, hey, the missing equations that you should have put in the first place is here, right? So this is what we call this automated physics discovery. So the scientific machine learning libraries are kind of this whole kind of connection where we say, okay, we want to give you solvers that are kind of like the solvers in MATLAB or SciPy, but they're faster, more robust, and they have this capability to mix with machine learning tools. So that way they can, do this automated physical discovery. And if you're interested in this topic, there's a lot of other talks that I give on YouTube that are specifically about this. In fact, an hour talk going into detail about how these things work is my normal talk, right? But what I'm going to go into here then is some of the new ways that we're improving a lot of the tooling along the solvers to be able to make this a lot better. So what I want to describe is the future algorithms, which, I would say about like 70% into it. A lot of these algorithms, everything I'll be talking about here today is things that you can already do, but there's a lot of next steps that we're doing in terms of the research here. So this is where I'm going to talk about what's all next. So we have solvers that are fast. We have, they're good numerical algorithms. You can differentiate them, add numerical neural networks to them and everything. But what's the next domain? First of all, I want to answer this question of why is there a next domain, right? If I go back to one of these, to a lot of these, right, you'll start to see that, like, okay, we did get a better numerical solver for this stiff ODE. This is this Julia-based Rosenbrock 2.3. It's an algorithm that you only find in Julia. It ends up being about, 5 times faster than what you find in like Sundial C for a large number of equations. That's good. Okay, making things 5 times faster is pretty good for stiff ODE solvers, right? But we start working on this a lot, and you start being like, okay, you get 5 times faster. The next paper is like 2 times faster. The next paper is like 1.5 times faster, right? It just, if you have to treat all problems the same and the only hammer is numerical solvers, it becomes very difficult to get much better. You start to converge to being able to say, well, it does better in this domain but not in this domain, and so coming up with general algorithms is hard. And so what we start looking at is to say, we're starting to saturate all of our improvements. What can we do to be able to stop saturating this? Well, maybe the way to do this is to change the problems that we're solving, or to be able to subset the problems better that we're solving, right? Even with the nonlinear solvers, right? Improving over Newton's method, you're getting improvements of, well, before it was like 10 times, but now we're getting like smaller changes, like 2 times faster, et cetera, like with all the newest papers. And so it's starting to saturate. So we need to do something different. We can't just keep on pounding on this idea of better numerical numerical methods, right? I know, like my background was numerical analysis. It's a great fun thing to study, but it saturates at a certain point. So what can we do to get past that fundamental issue, right? So what we've developed is a symbolic numeric system, right? Where what you can do is this uses symbolics.jl, which is a full computer algebra system, and so if you think like Mathematica, Maple or so, symbolics.jl is a completely symbolic system where you can do all sorts of symbolic solves on it, right? And what we can do is we can say, hey, let's define our ODEs using symbolics.jl. And then we could use something called modeling toolkit, which is this transfer layer that takes symbolic systems and generates code for them from them, right? So it takes this description of, the second derivative in x is equal to here and derivative y is equal. So it takes a symbolic description of the ODEs and then it transforms it. So it says, okay, lower the order of the system so that way I get a first order ODE system, right? So you use the trick that you say, V equals x prime. So you have 4 equations instead of 3. And so once we do that transformation, we can then generate code that we then give to the numerical solver, right? And so this is something where, before you might have told someone like, oh, if you want to use a solver for first order ODEs on a second order ODE system, here's how you write down the second order ODE system to work, right? But here we can say, oh, if we actually understand what your mathematical equations are, and we have a symbolic system, we can just automatically do that for you, right? We can just change your equations to work for the solver, right? So that's the first basic example to show the need for a symbolic numeric system, right? If you tell someone our ODE solver only works for first order ODEs, but if you redefine your ODE systems in a very specific way, you can use higher order ODEs with this, right? Instead of telling people the procedure, you could just tell them, hey, give the ODE system to me symbolically. I will transform it for you using this algorithm, and boom, now you can use the first order ODE solver on non-first order ODEs, right? And this is then a system where you say, okay, the models are given to me symbolically, and I have this layer that is modeling toolkit, that's this intermediate ground between symbolics and numerics, and I'm going to use a symbolic system and all of the different rule rewriters and e-graphs and Grosvenor bases and all these symbolic algorithms as in part of the process for me to be able to come up with new things. What it looks like when you put it, when in general ends up being this whole system where you say like, okay, I can have different forms. Like I can have differential algebraic equations, the Modelica form. I can have models coming from circuit models, from SPICE and things, right? And then I can put this into one form where then I have a compiler where this compiler is not like a programming language compiler. It's a compiler for equations where I can start to do things like say, I differentiate your equations and then I find structures in them and I can change the structures around. I can do state selection. I could delete equations, yada, yada, yada. And I'll go into the different parts of this pipeline. But what it really means then is that we can start to make things work. We can start to really change the equations before we end up solving them. And so the solver you don't need to do as much work in the solver, and you can make more assumptions in the solver because you can always change the equations in a form that the solver wants. So what do I mean by this? So let's take a look at a system, right? So here's a symbolically defined nonlinear system given in modeling toolkit, where the symbolic system here is u1 equals sine of u5, u2 equals the cosine of u1, u3 is the hypotenuse between u1 and u2. You can read out the whole system, right? So this is a nonlinear system. And if I was to ask you how you would solve it right now, numerically, you'd say, oh, I will go to SciPy and I'd put this in and I would call the root finding algorithm, right? And what it would do is it would use Newton's method, right, to be able to solve this system of 5 equations, or you do this in MATLAB as well. And it will find what are the values of u1, u2, u3, u4, u5, such that all of these equations are satisfied, right? That's your standard root finding problem. Now, the way that it will work, right, if you think about how Newton's method works, right, I don't know if I put, the way that Newton's method works is it will, right, you take the Jacobian of your system, right, it will be a 5 by 5 Jacobian. You then do an inverse of that Jacobian, right, which is O of 5 cubed operations. So it would take about 625 floating point operations to invert that or do the linear solve, right? And you'd have to do that every single step of your solve. So you're doing 625 floating point operations per step of Newton, and then you solve that, like say in 10 iterations, right? So yeah, that's one way to solve it. But if you look at this system of equations, you can actually do something very different, right? Like if you actually sat down and said, okay, I'm not going to trust the numerical algorithm to do everything. what can I do instead? Well, what you can do instead is you can say, well, okay, you can say, well, let me just move this to the other side, right? So U1 equals sine of U5, U2 equals cosine of U1, U3 equals hypotenuse of U1 and U2. Oh, actually, I've already defined U1 and U2, so that's perfectly fine. And if you do the bunch of substitutions, what you find is that, you only actually have one equation to solve, U5 equals hypotenuse of U4, U1, where U4 is defined as U2, U1, and U2 is defined as cosine of U1, cosine of U1 is sine of U5. If you actually plug everything back into the system, you find that you just have one equation in terms of just U5. Right, so you can numerically solve for U5, and everything else is actually just explicitly determined for the value of U5. And so you don't actually need to call the solver, the Newton method, with a 5 by 5 system. You only need to call it with one equation. Just this is the one equation you have to do. Find this equation and substitute everything back in, right? And so the key here is that, like if you were to be working on your one little problem in isolation, you might go, oh, I found this trick so that way I can make this easier and more numerically robust to solve, right? Again, it ends up being more numerically robust to solve because you're not numerically solving all the equations. Four of the equations are exact, if you do the substitution, right? You only have, and so it ends up being more robust, but it ends up being cubically faster, right? So you go from 625 operations to do the matrix inverse to one operation. So it's literally a 625, like you could know beforehand without even writing the program. It's 625 times faster to do it this way, right? So that's a pretty massive speed up. But now the question is, okay, if I was to tell you, like, find the fastest way to solve this root finding problem, you can probably sit down and say, okay, and do all these substitutions. But what we've been able to do now is we've been able to say, hey, look, if this is your symbolic system, I call structural simplify on this set of equations, right? And you can almost think about it as it simplifies the equation in a symbolic way. And what it returns for you is it says, this system of 5 equations is actually equivalent to numerically solving this system of 1 equation, where these are now the observed equations from this, right? Where an observed equation is an explicit equation given by the variable that's solved for, right? So we turn solve for U1, U2, U3, U4, U5 into something that is now solved for U5, and the other 4 variables are directly determined from it, right? And now with this system, so this is what it actually looks like as code, right? You declare a system of 5 equations, you then call simplify on it, and it gives you a system of 1 equation. Then you call the same numerical solver they solved before, right? This nonlinear problem and everything. This is the same exact thing that I said back here, the solvers, right? It's the same good solvers there, but now you end up solving where you just say you give it one initial condition, right? You give it the guess for only U5, it solves for that, and actually only solves for one value. But if you ask it for what U1 is, you ask it for what U2 is, it also generates those whenever asked, because it actually holds on to that information. So it's only solving, in order to solve these 5 systems, 5 system equations, it instead solves one different equation. And when you ask it, what is U1, it'll be able to be like, yeah, I know how to reconstruct that. It's just this value, right? But the solve is 625 times faster because it does not have to do an LU factorization of a 5 by 5 matrix. It instead is only solving a single scalar equation, and so it's using a much faster solver, right? And this is the key idea of the symbolic numeric method, right? You could, in these situations, sit down and do all these optimizations yourself, but if we allow ourselves to be able to expand what we do as the numerical method to say, I'm allowed to change your equations for you, I will change this set of equations into this set of equations, and I'll numerically solve this one, and then I'll convert back to the other one, and I will solve this a lot faster and more robustly than you could ever do with any numerical method. And once we realize that, we're off to the races, and we just say, this is a whole new class of algorithms. How do we do this effectively? How do we do this fast? How do we do the symbolic thing better, right? And what are the different ways we can do it as well? So one of the interesting places where this really comes into play is within side of the ODE solvers, right? So if you've ever learned like an ODE solver, like like Runge-Kutta methods, right? One of the ones that you learn is that implicit methods end up being more stable, right? So you do use something like implicit Euler. In implicit Euler, you have an implicit system, so you use Newton's method as well. Well, do you actually have to use Newton's method? Now that we know that we have something better we can do than just a Newton method, right? What happens if you actually start to do the symbolic numeric trick on the implicit solves that are inside of an adaptive order stiff ODE solver, right? So what we can do is we can take our good ODE solvers for stiff equations, we can yank out the internals that is doing a normal Newton method, and we can start to build kernels where for your given ODE, we actually do symbolic solves, we do the same exact symbolic thing. So you might have, a system of 50 ODEs, but our Newton method only solves for 3 variables, but is doing exactly the same solve using the symbolic numeric tricks, right? With this one I'm calling tearing, right? And what we show is that this actually works really well in practice, right? So on a system where you have 20 DAE, so this is for a model of a car catapult actually, so it's like a car system. We actually showed that you can go from like 18 ODEs, and you can turn it into actually 4 in one of the versions of the system, right? So instead of solving for almost 20 stiff equations, you can actually turn it into 4 almost non-stiff equations and solve that system of equations instead, and then give back the solution to the user. In fact, there's one even more intense case where we showed that prior to the system, we had 50 equations, and then we were able to transform it down to the internal solves of the system. The Newton method is actually only working on 11 equations. And if you go back again to the scaling of this, Newton's algorithm scales like O of n cubed. And so you go from a cost of 50 cubed to a cost of 11 cubed. It's a pretty massive speed up, and it ends up being more robust because a lot of equations are turned into exact equality through substitution. There's then a lot of other tricks that we can do, right? So instead, if we have parts of the equation which are defined linearly, then we don't actually need to resolve them inside the Newton iterations, right? What we can do is we could identify linear subsets and directly solve the linear subsets as well. This is an inline solver, linear solver optimization. This does 2 things. One is that we can cache that linear solve, and so we only have to do the linear solve 1 time. So we save ourselves the time of repeating it every Newton iteration. But the other thing that we get is that we can do this almost exactly, right? So we can effectively remove these equations from the system, and ends up being a lot more numerically robust. And so again, this is something that you might do by hand in some systems, but we can start to say, if we have a numerical method, you don't give us the function to run Newton on. If you give us a symbolic part of the system, we'll take out the linear part of the system, solve it once, and then only do the Newton solve on the nonlinear system. But even on that nonlinear system, we'll then even do all these transformations and make that even smaller, and then we'll solve that. And boom, once we start to do all that stuff, you can see how we can get to like 1,000 times faster pretty easily, right? We're not even playing the same game anymore. We're numerically solving much simpler equations that give you the same result. So of course we're going to win, right? In fact, we can even come up with even more intense algorithms. This one is really fun, where if you have a whole set of different ordinary differential equations, you can come up with different substitutions where smaller sets of ODEs actually fully recover the larger set of ODEs. This is called the exact ODE reduction. So in our ODE solver, we can look at, at a compiler level, we could look at what equations you're trying to solve, and we can change your function. We can actually use the compiler to change the function that we're numerically solving before you solve it, and then do some tricks in the library so that when you ask for the solution, we give you back the solution that you want, but we're not actually solving the right equations. We're solving a different set of equations because it's numerically easier. And with that as well, we can also then look at your code. Like, so for example, in this code, right, we can actually use a push-through trick at the compiler level and the symbolic level to identify what the sparsity pattern of your Jacobian is. There's a really nice algorithm to this. I can point you to the paper if you're interested. But basically, for any function that you give us in the Julia language, we can automatically just deduce what, if you're to put this vector in there, then the sparsity pattern of your Jacobian is this. So our solvers then don't need you to pass that information in. We can directly look at your code, find out which variables touch each other, right? Like, oh, this variable and this input and this output are in the same equation, so you have a non-zero in this sparsity pattern. But if you're 2 over, then it's not in the equation, right? So we're able to use the actual code to find out whether it is even possible for this input to ever affect this output. And that is your sparsity pattern, right, of your Jacobian. And then we can directly in our numerical algorithm say, let's always use the sparsity pattern of your system because we can compute it ourselves. So we don't need to ask the user for it. And so as systems get larger and larger, we can start to specialize on this and get really fast solves. And it's almost cheating, right? It's almost like, oh, in MATLAB, you should have passed the sparsity pattern. Or like should have, would have, could have, but we do it automatically, so you don't have to care, right? One last little thing is with differential algebraic equations. I think I'm running out of time, and so I can't go through this example exactly, but it turns out that if you write down some differential algebraic equations for numerical solvers, like for example, here's a pendulum in Cartesian coordinates, in the standard way that you would write this down, where you say, oh, x squared plus y squared equals L, right? The pendulum lives on the line or on a circle. It turns out that numerical solvers have a difficulty solving this, but if you differentiate this equation 2 times and substitute in the other ones, you rewrite your equation like this, and this is actually numerically easy to solve. So this is something called DAE index reduction, and we can also then do this as well. So we can do this kind of transformation. We can look at what the physics of your equations are. We can differentiate and actually move things around. This is an equivalent formulation. You probably would never write the pendulum in this form, but it's actually easier to solve this form, and we can automatically deduce what is the formulation of your equations that is most numerically robust to solve. Transform your code into this one and do that automatically. So here's a code where, again, this is actually code that's given not symbolically at all. It's just as a function in Julia. But what we can do is we can use the compiler to actually inspect the function that is actually given a sparsity pattern and graph of interactions. We then apply the symbolic algorithm to change this equation right here into that other set of equations, and in that other set of changed equations, we end up getting a stable solve. Whereas before running that, you end up having the DA solver ends up diverging. So it takes a lot of detail to describe everything in there, but this is really the key of these symbolic numeric algorithms, right? We can take your code that you give to us and just say, I understand what you're trying to solve. I'm not going to actually run your code, though. Like, your code is more like a blueprint of what mathematical equations you want to do. I'm going to then change your equations into something that I know is going to run better. I'm just going to run the better thing and then give you back the solution because I know how to map between the two. And it turns out that once you allow yourself to do that, your numerical algorithms just improve a lot because, well, you're no longer playing the same game, right? You turn hard problems into easy problems. You just solve the easy problem instead. And so there's a lot that we're doing in symbolic numerics and a modeling toolkit. A lot of things where, automating Laplace and Fourier transforms and doing all sorts of different tricks. So for example, another thing you can do is like uncertainty quantification, right? Instead of having to do Monte Carlo sampling over a large parameter space, you can actually find a new set of ODEs that would actually be the push forward of your probability distributions and just solve one set of ODEs and then fake doing a Monte Carlo simulation just by knowing knowing the probability distribution that you'll end up with, right? All sorts of different tricks here, but the key here is like this idea of these are algorithms which are not just doing the numerics, where we are purposefully cheating and changing the system before solving it, and there's so many different cool things you can do here, and we believe that this will be the future of where the code is going, right? Not that I don't want to work on numerical algorithms anymore. I'm definitely going to keep on publishing there. But if you want to get what is the next 1,000-fold increase over your standard Runge-Kutta method, it's not going to just be better Runge-Kutta methods. It's going to be one of these things that includes symbolic numeric tricks in there. So I can end there because I think that's the end of my talk. If you have any questions, feel free to ask.
Okay, thank you, Dr. Rackauckas, for a very great talk. I enjoyed it a lot. Before letting other people to start asking you questions, I'm going to start myself. I have a memory with Julia. At the end of my PhD 2018, I was writing something with Maple, and we do things with chemical reaction networks, the complexity go high. And then someone told me that Maple has a lot of control things in the background. If you do it with a simple programming language, it will be faster. So I tried Python, it was 10 times faster. Then I heard about the advertisement of Julia that as easy as Python, but fast as C++. So I did with that. It was 100 times faster. So in total, 1,000 times faster than using a Maple. But with things that you told today, I think I have to go back to Julia after several years, and I think it will be even faster. But my question, so the part of talk about structural simplify reminded me of something that my PhD supervisor was doing. So we do this chemical reaction network steady state polynomials, and you are looking at the positive solutions of when you were using mass action polynomial things. we have a lot of parameters and variables, but sometimes my PhD supervisor could look at the graph of the reaction network and say the positive solutions of this system is in one-to-one correspondence of positive solutions of a univariate polynomial of a very nice form. She was doing it by her mind, and then she asked me if I can do it automatized. I tried several things. The closest thing I could find was the univariate rational univariate representation Ruhr algorithm from Fabrizio Rulli. I don't know if you're familiar with that, but it was not working on the class of network that we were working with, so I failed that. But I'm interested to know how structural simplify of your things is working, and that can be something interesting.
Yeah, well, that's a very long topic. What it did is I did run a short course at MIT during January that showed that there's more interest to actually get this all written down. So basically, if you look at this modeling toolkit course, these are notes from the 18.S191 special subset in mathematics that we did for this, right? And it goes through a bit of the new symbolic numerical methods up to some of this stuff that I talked about with the stabilization through Pantelides algorithm and such. So these are some course notes I put together. It was just a 1 month course, so I realized from that there's a lot of interest. So I'm going to have to write down a lot more notes, but at least this is a starting point. So I'll point you to, if you go to this short course, it goes into some details. I'm going to have to write down a lot more.
We look forward to that. Okay.
But specifically for chemical reactions, there's this stuff that we've been developing called catalyst network analysis, right? So I think in 2018 we didn't have this catalyst.jl, but what we do now have is we have a whole system for modeling chemical reaction systems, where you put in everything in this chemical reaction system form, and it's able to then build the Gillespie model, the ODE model, the SDE model, and all these different forms, right? We've had a project going on for a while now, which is it can actually analyze these networks and be able to do things like derive what the conservation laws are, be able to derive certain properties of the steady states. So it uses something called residue theory and such for being able to do this analysis. Again, this library is not 100% ready yet. A lot of this symbolic numeric stuff is kind of on the edge, but at least but it's able to do a lot of proofs of these kinds of things, be able to tell you like, oh, here's how many steady states your system has, and it's able to do all this analytically to then be able to inform the solvers a lot. And then you can actually use special solvers once you have that information. So special homotopy methods instead of Newton methods can actually be more efficient there. So specifically for chemical reactions, you might want to look into this a bit. And I think a lot of the papers and stuff that I think are inside of the pull request. Or they should be. I mean, we'll have to talk with Vincent where if he's documented some of that yet. But yeah, so there's a lot there to be able to share, and specifically in chemical reaction systems. Because I mean, actually, let me also share a blog post I wrote earlier this week about this kind of topic, right? Where basically what you can do, so here's a chemical reaction system, right? What you can do automatically is you can start to use these kinds of tools to say, if this is the ODE system that I have, right, I can go from this version of the ODE system, realize how things add up. And so instead of using this form, I can say, oh, this actually has a conservation law. And then once you have a conservation law, you go, oh, actually y3 equals y1 minus y. And so you can actually then turn it into a set of 2 ODEs instead of 3, and it's much easier to solve, right? So I'll give you the link to this as well, like all the different ways you can look at these systems with hard constraints. But yeah, so with chemical reaction systems, you can basically start to build these symbolic tools that actually prove all these relations between them, and you can just get rid of tons of equations because of the conservation laws and positivity and all these other assumptions that chemical reactions have. So that's definitely one space that we're going to do a lot more, and you'll see some papers in the near future. Not all the papers are ready yet, though.
So I think I should let the other people also ask questions from the audience. Anyone has a question? Alexander?
But maybe before there were some things written in the chat. Let me see.
That was the Dr. Rackauckas sending the links.
No, but also Tereso before that. Also, Tereso.
Yeah. Well, the question here: how do you identify the relationships between equations? When do you stop looking for simplifications? Yeah, that is the much deeper part. Which I'm just going to say A lot of that is this Haring algorithm, which is described in full detail. I believe that the Haring algorithm is described in lecture 8 of these lecture notes. So I won't, I give that as a 2-hour lecture, so I didn't even try to put it into this talk. But if you go through the lecture notes, this should be good, and I'll be coming out with new videos in the near future, specifically going through how a lot of these algorithms work. But basically, I want to give a primer as to like why we're in this research direction, what we're doing. But yeah, the full description of how do you do these algorithms. I'll tell you that the graph algorithms at their core, right? You build an interaction graph between the different things, and you turn it into these like maximal coloring algorithms and things like that, right? But how to actually turn them into graph algorithms is like the tricky part. Like if you just look at it as a system of differential algebraic equations, you're like, okay, but how do you actually how do you actually get a coloring problem out of this, right? But it turns out at the end of the day, they turn into graph problems. It's just the showing that solving this graph problem is equivalent to finding the maximum number of simplifications or the optimal tearing result and stuff. That's then where all the core mathematics is. And yeah, there's no way I was going to fit into this talk, so I'll just give you the sources to go find more for now, and hopefully put up more videos on this pretty soon.
Maybe I can ask. I mean, in this direction, the one that Tereso and you just mentioned, yes. And since you mentioned the differential algebra, are you using in these equivalences or techniques? Yes. Are you using techniques from differential algebra and differential algebraic geometry to construct this, more involved techniques from there to simplify them and to systematically obtain the equivalences?
Yeah,
Some of the
things in the some of the things in the exact ODE reduction algorithm, it is a pretty deep in the differential algebras formulation. So the exact ODE reduction is one that, yeah, if you look into detail with what Alexander had done there and such, it is all baked in differential algebra, and the solve in there ends up being a Grosvenor basis solve, where you're solving for the ideal of this differential algebra, yada yada. So it's computational algebra in that ring theory type of form. That gives you these kinds of solutions. That's also true for one of the other parts of the code that I didn't mention before, which is structural identifiability .jl, right? So one of the things I didn't mention is this kind of, so you have this problem where you can say, like, okay, if I have like these lockable equations and I only observe x1, right? Then which of the parameter values am I actually able to observe, right? This is something that you can start to say like, oh, B is not identifiable because for any B divided by lambda, you get the exact same looking ODE solution in terms of x1, right? So if you only observe x1, then this parameter cannot be known, right? And it turns out, so then you can have this inverse question of, oh, given this kind of information, can I know exactly what parameters I can identify and which parameters I cannot identify just from knowing what I'm going to observe, right? And this is another problem that turns into a differential algebra problem that you get a Grosvenor basis, and it can tell you, identifiability and such. So a lot of these problems turn into like this, ring theory kind of problem at their core.
Very nice, thank you.
So there is a question in the chat from Mashal Nagin. Do you want me to read? You want to read yourself? Should I read it?
Can symbolic-numeric methods, particularly with tools like Modeling Toolkit, be used to assess or improve structural identifiability of dynamic models? Oh, I guess I just accidentally solved that one. Yeah. So structural identifiability.jl is a structural identifiability system that uses the same symbolic system as Modeling Toolkit. So there's a tutorial in Modeling Toolkit that shows you how to connect the two. I believe it's parameter identifiability of ODE models. So it shows you like, okay, if I write down this system of equations, which it can come from it can come from the catalyst system, right? So you can write down a chemical reaction system, it turns it into an ODE system, and then from that system, you use the structure identifiability. You have to tell it what are your things that you can observe and such, and it can tell you what's locally identifiable and what's globally identifiable. So locally identifiable means globally identifiable means that there's only one parameter value that you could have, right? Locally identifiable means that there are finitely many solutions to the parameter value, right? So non-identifiable means that there's a whole, manifold on which the parameter works, right? So it's like, oh, as long as A over B equals 1, then you get the same solutions for these observed, right? So it's able to tell you, like, are you in this case where you have infinitely many solutions for the parameters, finitely many, or 1? Though being able to prove that there's only one, the global one, is really computationally expensive. I think it's O of n to the fourth. So generally we tell people to only run the local identifiability one. But yeah, this is all stuff in the system that you can make use of. And yeah, we end up using this a lot in pharmacology. That's one of my backgrounds, right? I have a pharmacometrics background, and we have actually integrated this into the PUMAS tool for pharmacometrics, so that way you can kind of be more definite on when your parameters are correct or not. And we give this out as one of the pieces in the report for the FDA.
So there is another question, I think, from Saib. You can unmute yourself and ask your question.
Yes. Hi, and thanks for your inspiring presentation. I have a question. Do you think there is any numeric algorithm that can speed up Grosvenor basis computation, which is symbolic?
Oh, that is a very good question. Yeah, so because so you can start to ask the question, can you go the other way around as well, right? And I didn't touch that in this talk. So what we actually did a little bit of is a Symbolic-Numeric integration.jl. Which is this funky library where what it does is it's a symbolic integrator, right? So you give it a symbolic set of equations and it integrates it and it gives you a solution, right? But the way that it works is not symbolic at all. It works numerically. So what it does, so the way that the symbolic and numeric algorithm actually works, right, is, so I mentioned somewhere earlier in this talk, right, that we have tools for doing what's known as symbolic regression, right? We can find functional forms from data by training neural networks and then doing this kind of this symbolic regression kind of approach, right? So the way that the symbolic numeric integration library works is it basically does a numerical integration on some basis decomposition of the integral, and then it does symbolic regression on that to then give you back out what the basis of the solution is, and then you just have to find the coefficients of it. So it's using a numerical method to solve a symbolic problem. And if you're curious how that works, I can point you to the paper here. We ended up publishing this recently, but the archive is always the one that's free, right? So I'll just send you the archive. So yeah, it kind of goes into detail on how this is done. So we definitely have worked on this case, yeah, where you say, okay, I want to solve a symbolic problem, but here's a numerical algorithm that can solve the symbolic problem. And I wouldn't say that it's always better, right? Like the symbolic algorithms have, the symbolic algorithms are much better at saying, like, oh, if you have 1/2 in the solution, this might tell you 0.5 instead, which, all right, you might lose a little bit of precision. Also, it can't find all the solutions, but it can shortcut itself into finding the solution of very difficult integrals. And with so some things that you find really difficult to do with like the Riesz algorithm, like the symbolic integrating algorithms, can actually be easier sometimes with the numerical one. They have different problems that they find good, hard, and easy. And also, like, this will also fail on some easy integrals, right? So it just has a different space of what you find hard and easy. And so definitely when you go to this question of like, okay, could you do something similar with Grosvenor bases, right? Can you come up with a numerical algorithm that gets you quicker Grosvenor bases? You probably could. And that would be a very interesting research project. I don't know of anyone that's done that, but that's definitely something that we would be considering along these lines of these symbolic numeric algorithms. So yeah, that's a very great question. And I'll definitely have to hopefully, if you give me a few months, I'll have to see if I can come back with an algorithm.
Thank you so much.
So on the mixing this symbolic and numeric methods, I had one work 2020. We had a CAD of a system with 3 variables and 2 parameters, but we wanted to decompose the parameter space 2-dimensional according to the number of positive solutions. And it was not working with all 3 together 5 unknowns as symbol. The trick that we did was we put value for one of the parameters, so it become 4 unknowns, the complexity goes down, and the result become like a line intersection with the 2D picture, and then kinds of smart bisection search one to find the place that the intersection changed its behavior, and that was working very fast. So using these symbolic numeric things to help each other is nice, especially if you reduce the number of unknowns, they speed up everything.
Yeah, well, and that's what I was kind of mentioning when kind of introducing it, right? That I think everyone kind of does this already on hard problems, right? When you run into a hard problem, you go, oh, the numerical method doesn't work. And you kind of think about how do you solve it for your specific case, right? And really what we're trying to do here is just say, can we just make the software do this automatically? Like what needs to be, what are the symbolic problems that we need to solve such that we can build software that does that automatically is the real question, right? So, and it must be possible because like in every case, the PhD student has graduated, they probably had to do something like this on their own model, right? And so it's just a question of, can we just gather that knowledge into some automated form, right? So that it's been a fun project because you end up getting some things that just go, all the things that you knew, but like you no longer need to do that, right? The software does that. It's just more like coming with a list of what are the hard problems and how can we find out what tricks you're actually doing implicitly when you're doing it, and can we codify that into an algorithm?
Any other question from the audience? Well, if not, let's thank Dr. Rackauckas again. It was a very interesting talk.